So just gotta try it twice for no apparent reason.
Test, test, test. Test, 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 test. Do you have audio stream? Test, test, test. Audio. Testing, testing. All right. Oh, you hear the snares? What do you hear now? Any better? I can't believe. I mean, the mic is a little directional. You don't have to run outside.
Barely.
Test, test.
Go forcing something if it's just not right. No time to search the world around, 'cause you know where I'll be found when I come around. Time to search the world around, 'cause you know where I'll be found when I come around. When I come around. When I come around. When I come around. I'm all busted up, broken bones and nasty guts. Accidents will happen, but this time I can't get up. She comes to check on me, making sure I'm on my knees. After all, she's the one who put me in this state. She don't survive it if she disturbs the melatonin. Before she does it all over again, know that she's killing me. For now I ride around, well that's all I can really do. She takes good care of me, just to say my love's true.
Is there no settings there? Can you tell? Okay, test, do I have audio? You can hear me, Michelle? Yes, so, Michelle, Melissa, whatever your name is over there. Hi, everybody. We're all here, back and ready to go. So, yesterday we were talking about electronic transitions, and we talked about how electrons fill orbitals, and when they're in orbitals, how transitions occur between those orbitals, and the energy spacing in those transitions gave us the various spectral lines, the various emissions from atoms and molecules. We talked about how electrons have this property of spin that allows them to occupy the same orbital. So in general, we have the Pauli exclusion principle that excludes matter from occupying the same space. But if electrons have opposite spins, they can occupy the same orbital. And you can, that's often described as a fourth dimension. It's a fourth quantum number. Sometimes people say, well, if you're sitting in a chair, you can sit there, but someone else could sit there if you got up. So that's a time variable. You're in the chair, you get up, and someone else can sit in the chair. The electrons are actually much more interesting than that. We talked about this property of spin being a acting like a magnet, but the electrons aren't actually spinning and creating a magnetic field. It turns out that this spin property is intrinsic to matter. So it belongs there. It's not a magnetic effect or a spinning effect per se. In fact, if you solve quantum mechanical equations, the quantum mechanical equations were solved in the 1920s. And this physicist, Paul Dirac, came along and he said, well, quantum mechanics isn't quite hard enough for me. I'm going to incorporate relativity and quantum mechanics together. And when he did that, a new formulation of quantum mechanics came out. And in that, there was a mathematical step, a mathematical result that was inherently this spin characteristic. That is, you didn't have to do any special math. You didn't have to add spin to the quantum mechanical equations. It was naturally there. So it's a natural property of matter. And if you cast quantum mechanics in terms of quantum mechanics and relativity, it's a natural property of the equations. We saw that a natural property of quantum mechanics was when you put boundaries on a system, you got standing waves. That was just a natural result of the math. It turns out that spin is another one of those natural properties of the math. It just emerges from doing the mathematics in the correct way. So it belongs there, but it does allow electrons to be in the same orbital. And this spin is kind of a anti-symmetry. Electrons, they have this symmetry. Most things, when you go around in a circle, they come back to the same place. For an electron wave function, you go around the circle once, doesn't come back around to the same place. You have to go around 2 pi to get it to come back around to the same place. And that extra phase, that extra degree, that extra degree of rotation, that extra phase parameter is what allows the electrons to be simultaneously in the same orbital. You can think of it as a little twist in space. Electrons live in a 4th dimensional twisted space. You can think about it. Here, I've got an idea. Hold on, everybody take off one second. If I take my belt and I put a twist in it and then put it together. Oh, wait. we have these little eraser, little eraser things for the board. I'm going to put an eraser thing on my belt and then put it together with that twist in it. Stand by. Impromptu demo. Okay, so here's an electron in its weird space. If I have the electron here, you see this side is facing you. If I let the electron go all the way around this path and come around 360 degrees, when it comes around again, the other side is facing you. Goes around again. Sorry to get past the buckle. And that side is facing you. So that took 2 pi revolutions for that to come back to the same place. And you can imagine if I had 2 of these and I put one facing that way and the other facing this way, they essentially occupy different regions. Their wave functions are such that they can overlap in that same orbital because of their anti-symmetries. Their symmetries are opposite each other. So those guys, one lives on one side of the belt and one stays on the other side of the belt, and they can exist in the same wave function. So it's not really a magnetic property per se. It's not really a spin property. It's a property of space and matter that is naturally there. All particles that are spin 1/2 have that property. We talked about spin 1 integer spin and half integer spin. Those are different kinds of fundamental particles. The spin 1/2 particles have this property where they exclude each other from space, but their wave functions they can occupy the same orbital. The spin 1 particles have this property. They don't have to follow Pauli exclusion. So spin 1 properties can occupy the same wave function at the same time, and they can condense on top of each other. Electrons are away from each other, spread away from each other all the time because of this twist they have in space. So it's one of the interesting things about quantum mechanics. There's a lot of weird properties, and spin is certainly one of them, and it's one of the entertaining things to read about and talk about if you go on in chemistry or physics or whatever. It's all the same in the end. So let's do, we did this chem quiz, didn't we? Or did we stop there? Atomic, we did it? No, I don't think I did this one. Okay. So, actually, let's think about this one. Well, where's the question? Oh, there it is. So, for which atom does the plot here, so this is one of those photoelectron plots, depict ionized electron kinetic energy versus frequency? So this is the normal photoelectron plot. We're asking, here's hydrogen in its 2p orbital. Here's helium, also in excited state. The outermost electron is in the 3p. Lithium in an excited state, the 4th principal quantum level. Which of those, and for this, you got to kind of think back everything we've showed you so far about absorption and emission. Let's talk about this one for a minute. Go ahead and start the capture. So I can go ahead one and I can show you the group of 4 to help you think about that ionization of those atoms. Okay, am I back? Am I live? Am I back? Am I back? Okay, I'm back. So maybe you were thinking about this one a bit. Let's see what you're thinking. What Ryan has in the vote. Pretty much spread out a few more for B than A and C. And this one, I didn't expect you to just get right away. This is something you had to sit there, scratch your head, look back at that group of 4 information slides, and you could kind of look here and see what I was talking about, but I'll go through it with you. This wasn't meant to just be a stumper or anything. It was just go back and think about the whole big picture. So what we have here is hydrogen, helium, and lithium. But we talked yesterday how the inner electrons, the s electrons, are very effective at shielding the outer electrons. So there's positive charge at the nucleus. There's electrons around the nucleus. Does this electron out here in a higher principal quantum level see that full positive charge, or do those electrons in closer to the nucleus shield it? And indeed they do, and s electrons are very effective shielders of the outer electrons. Electrons in the same orbital don't shield each other very well, but if you're out a principal quantum level, or you're out an L level, so s orbitals, electrons in s shield p electrons pretty well, and that shielding is kind of what we're getting at here. So this is hydrogen, 1 electron, but the electron is in the 2 n = 2 level, 2p in this case. This helium, it has its 2 electrons. One is in the 1s and one is in the 3p. So it's in an excited state. But that 1 electron in the 1s is an effective shielder of that in the 3p. So this electron out here in the 3p, maybe draw a little picture. Here's helium, the helium atom, and it has, we know, Z equal to a +2 charge on the nucleus. So here's the helium nucleus with its positively charged protons, and there's an electron in the 1s, and then there's an electron out here in the 3p, and that electron out here, its charge that it sees at the nucleus isn't the full +2. It's more like +1, because this electron here is kind of canceling out, its minus is canceling out one of those pluses. So this guy effectively sees +1. So we call that, for this electron, Z effective is more like 1, even though the nucleus has 2 positive charges. So that electron shields the charge from this electron, and that electron in the 3p sees more like 1 positive charge. So effectively, this is going to behave just like hydrogen in a hydrogen atom, where its electron is in the 3p. Same thing for lithium. It has its 2 electrons in the 1s, shielding the electron in the 4p. So this 4p electron sees effectively 1 positive charge, because lithium has 3 protons, but 2 of them are fairly well shielded from 2 of them shield those positive charges from the 4p. So basically, it's a hydrogen in the 2p, it's a hydrogen in the 3p, or a hydrogen in the 4p is how those species behave. So what does that mean? We drew this picture and we said, what does this ionization scheme look like? Well, this says that you need ultraviolet radiation to just ionize the this atom we're talking about. And what that looks like from this picture, as you can see, is here in the 2 level, you can see red isn't quite sufficient, green isn't quite sufficient, blue isn't quite sufficient, ultraviolet gets you here, and if I keep going ultraviolet, I will eject electrons. So this plot kind of looks like, here are those red and blue and green lines. When you get to ultraviolet, you start to be able to eject electrons, and then beyond here, you can eject electrons. So if you were up here in 3 or 4, then it would just be red or maybe just blue would be sufficient to ionize from these 3 and 4 levels. So the level 2 is what it would take for a ultraviolet photon to kind of be the first one that would ionize the species. The frequencies below that would not. So that's ultraviolet radiation interacting with the hydrogen atom. We had some music playing on the way in the beginning. I don't know if you guys were here. Are you guys familiar with Green Day? I can't see what you're saying. Are you raising your hand? Band Green Day, local kids. They started here in Berkeley. So their song "Pulling Teeth." We can we cue it up again and play it? I'll see. I've got it. It's of course on my playlist. Here it is. I think I have to put the mic near the speaker because otherwise the mic, you just hear me. Stand by. So I'll start playing it for you here. When I heard this song the first time on the radio, I'm driving down the street, and it sounded like they were singing about ultraviolet radiation. And I was going, oh my gosh, cool. There's some Green Day bringing it home with the science. I'll play a little clip here where it's where they say that, and I'll get the mic next to the speaker for you. So here that is. I don't know if you could hear that. So great, Green Day with their ultraviolet lyrics. Could they hear that on the broadcast, do you think? What's that? Kind of. So it sounds like they're saying, is it ultraviolet? And they're not saying ultraviolet. They're actually saying ultraviolent. It's a song about abuse, unfortunately. However, when I was listening, it sounded like ultraviolet. So me, just like Ryan, I thought, well, maybe you could write the whole lyrics around that tune. So, and actually, this is funny. Billy Joe, he just lives up in the hills here above us in the East Bay Hills. So I figured I'd just call him up and say, do you want to collaborate and write a song? So I call him. I go, hey, Billy Joe, Mark Kubinec from the chemistry department down on campus. Your song "Pulling Teeth." It sounds like you're talking about ultraviolet radiation. It'd be fun to write a collaborating song and it's parody lyrics. And he goes, who is this? And I said, Mark Kubinec from the chemistry department, want to write a song. And he goes, how'd you get this number? so, so I had to write it on my own, is the short story.
Why
So
didn't you tell me ahead of time?
so we have it here. Here are the lyrics that I've written. And I guess you couldn't hear it very well here. If Ryan had her guitar, she'd play it for you. But I can sing it, I guess. So Green Day, Pulling Teeth, science lyrics. I'm all busted up, broken bonds I've come undone. Radiation will happen, and this time I've absorbed some. It's incident on me, and it's H nu equals E. Can't you see it's the one that has me in excited states? Here it is. Is it ultraviolet? Am I perturbed? I better emit some energy in the form of a photon or two. You know it's H nu equals E. For now, I'll all around in my ground states where I'm found. Radiation can't touch me. Everybody sing along with me. Unless H nu equals E. So go ahead, Google it, play Pulling Teeth by Green Day. Sing along with the science lyrics when you're at home and no one's listening. So let's move on to our discussion of the periodic table. So we understand now a lot about how electrons gather around positively charged nuclei, and they gather in a very organized way. And that organization of the electrons leads to a organization of the elements, because elements are species with increasing numbers of positive charges, and therefore increasing number of electrons to balance those positive charges. And the electrons are organized. They each have their own set of quantum numbers. And that leads to an organized state of all the elements in the universe that we know about. This periodic table is a little outdated, but it's not too bad. But the structure of this reflects the quantum mechanics that we have already discussed. So how's the lighting?
It's because it's all white. So the periodic, you can see it.
Oh, the periodic table is clear? Okay. Yeah, you don't have to see me. It just looked like it went black from my my view. So here's the periodic table, and the structure of the periodic table is reflective of quantum mechanics. And you can look at it this way. You have hydrogen and helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and you can see a structure you might recognize. You have two elements in this first row, and then when you go down to the second row, you have 1, 2, a group of 2, and then 1, 2, 3, 4, 5, 6, a group of 6. And that might remind you of something. That might remind you of, let me write a little bit on here. That might remind you of the N. Why did I write an A? That might remind you of the N equal 1 principal quantum level, where you can have 1, 2 electrons, and you're done with that principal quantum level. 1s1, 1s2, and you're done with that principal quantum level. When you go to N equal 2, you had 1s or a 2s electron, then another 2s electron, 2s1, 2s2, And then you had to go to the p orbitals, and you had p1, 2p2, 2p3, 2p4, 2p5, and 2p6. And then you filled the entire n equal 2 quantum level. So you'd go to n equal 3, just continue doing that. And again, 3s1, 3s2, and 3p6. You can keep going, 4 now, and now 4s, and then the 3d orbitals. Remember, the 3d and the 4s very close in energy, and in many elements, the 3d higher energy than the 4s. That's reflected here. The 4s electrons fill, and then this block has 10 elements, reflective of the 5d orbitals. So I think I've blocked that out here. So the s orbitals filling here, the p orbitals filling here, and the d orbitals filling in the middle. And down here, those are the f orbitals, 14 for the 7 f orbitals. And they, I thought I silenced that. That's my phone. You guys probably can't hear it. That's good. So the f orbitals, and they start filling in kind of in here in the middle of the d orbitals. So the actual filling, when you're up to the d's and the f's, those orbitals start coming very close together, and d's and f's are filling in the in a sequence outside of, you can't quite fit them in there, so we take them outside the periodic table. So you fill your d's, you fill your f's, and then you go back to filling your s's and your p's. So it's not a very good picture of how that happens here. I'll get a better periodic table for you next time where we can look at how the f's insert into the main periodic table. But SPDF, we understand the structure of the periodic table reflects quantum mechanics. And here's another one of those things that turned out to be kind of amazing. You probably know the periodic table is ancient. It goes way back. The structure of this periodic table, having the elements in columns, dates way back to the era of the alchemists, the 1500s, where elements were being discovered and their properties were somewhat similar. So chemists began arranging the similar properties in columns. And now we kind of understand why they have similar properties. They have similar properties because they have similar outer electron configurations. This carbon has 2p2, silicon 3p2, germanium 4p2. So from the outside, they look like 2p electrons is their highest occupied state. So their similar properties come from their similar electronic structures, but no one knew what electronic structures were there for sure. But it turns out then, after hundreds of years, we added quantum mechanics, the quantum mechanical formulation, and lo and behold, that fit exactly the almost ancient periodic table. So another of the triumphs, basically, of quantum mechanics was, oh yeah, that structure makes sense. So let's talk about some of the things we can look at the periodic table, some of the trends in properties on the periodic table. Ionization energy and electron affinity. We've talked about ionization energy already. ionization energy is the energy it takes to remove an electron from an atom completely, or a molecule. You have to put energy in for that to happen. So if you talk about a atom with an electron, you have to put energy in to get to the separated state. So I go from low energy to high energy, and the low energy is when they're very close together. They've got that strong attraction potential energy. You have to put energy in to pull them apart. You can put it in photons for the quantum levels, but when you put in more than that, you pull them all the way apart. So that's ionization energy. This electron affinity is also related to electrons and nuclei. Slightly different. We'll define ionization energy as the energy for this reaction that I just showed you, a neutral species going to a positive species and a free electron. That's ionization energy. Electron affinity we define by what is the energy released, the energy of this reaction when I force an electron on to an already neutral atom. And it turns out you can do that. There is a positive nucleus there, and this reaction often releases energy. So this state can be this X minus, the state with an extra electron, lower energy than the free electron and the neutral species. And one way to think about that is, well, these two things are apart. You have to think about the energy of the entire system, which is the neutral species and the electron. Put those together, that is a lower energy combination than when you have the separate species. So here's a table of some of those. So here are some elements. They're ionization energies. And you can see those are all, I've written them all in green. Those are endothermic reactions. I have to put the energy in. The activation energies here are exothermic, so I've written them with their negative energies. In this line here, there's a little bit of when you're reading about electron affinity, there's often a little bit of confusion. It's defined as the energy released when you bring an electron and a neutral species together. So I've written them as energy released, and I've put the negative sign in there to indicate that that's exothermic. So we can actually look at ionization energies. Let me discuss this a little bit more. So here's one of those metals, M, and I'm going to add it to water and do this reaction. The metal plus the water forms hydrogen gas and the metal hydroxide, MOH. You can think about that in two steps. It's a redox reaction. We'll talk about that later. But the two steps are the metal losing the two electrons, so double ionization, pulling the electrons off, happening at the same time as water accepting those two electrons, forming hydrogen gas and the OH minus ions. Those two reactions happening at the same time. This one we know is endothermic. I have to put energy in to pull those apart. This one is exothermic. Energy is released when that happens. I can add them together, of course, to get this reaction. And whether this reaction is total reaction is exothermic or endothermic depends on the relative energies of these two. So what we can do is look at different metals. This reaction, this exothermic reaction, has the same energy regardless of what metal we put in the water. So if we put different metals in and we see the energy of the reaction, we can tell learn something about the ionization energy. So if the ionization energy is very high, then this requires a lot of energy. This releases energy. But if this requires a lot, the energy released here will be used up in this endothermic process. So if these are equal in magnitude of energy, the energy required to do this is the same as the energy released when I do that, this total reaction will be kind of boring. But if this is easy to ionize, low energy here, I still get the same energy here. So the easier you are to ionize, the more overall energy will be released because you'll have excess energy from this reaction happening that will be released. So Lonnie does that for us in the demo lab, of course. So let's look at that. Come on, give me the full screen thing. Okay, so here's Lonnie in the demo lab. How does that look? Oh, that looks fine on the webcast. He's going to drop in sodium to water. And we'll zoom in on that. You can see the sodium is just kind of bubbling around. Well, that wasn't a very good zoom in. Sodium is just bubbling around here. It's floating on the top. There it is. It's just floating on the top of the, and you can see it's making that hydrogen gas and just floating around, bubbling around that sodium metal on the surface of the water. Now, if we go to potassium metal, he's going to take that potassium out and drop that in the water bath. And now in this case, we'll see a more vigorous reaction. So we'll zoom in on that. This one is producing hydrogen more rapidly, and that ball is floating around and zipping around the tank a little more energetically. That means potassium was easier to ionize. So the energy released by the water reduction reaction was a little faster. Now he's going to put, okay, so, whoa. So he jumped ahead before I could say. He put the next element down, rubidium, and the rubidium, the ionization energy is very low. So all that energy released from the water reaction is released dramatically. Now he's going to go to francium, one more down, and he's put on all the protective gear. So you can imagine that this last reaction will be even more dramatic. So that actually explodes because the ionization energy of francium is so low that all that energy from the water reaction, the reduction of the water, is released. So that's kind of fun. I should probably make sure that just doesn't sit there and run. Go back to our PowerPoint. So one of the disappointments, of course, of summer session is if we were all in Pimentel Hall, we would be doing that stuff live, and that would be much more fun than watching the YouTubes of the demonstrations. But Lonnie and I worked together for many years. We put together those demonstrations. I'm glad we recorded them in the studio. Turns out COVID-19, good call. Now we can show them to you in the studio, but I wish we were in Pimentel so we could show them to you live. So what we looked at was the sodium, then the potassium, then the rubidium. And you can see their ionization energies decrease. The rubidium easier to ionize. We even looked at francium, one more down the periodic table. So we're going down the periodic table. Ryan, can you, on your PowerPoint, bring up the first slide periodic table so I can jump back and forth? So we're going down a row of the periodic table, and we have we'll have that periodic table back here. So we looked at the ionization of the sodium here, and that was kind of boring, just kind of buzzed around. Potassium, that fizzed around a lot. Rubidium, even easier to ionize, that actually exploded and was that slow motion explosion we saw. And then we didn't have cesium, and I'm not sure why we couldn't get cesium. We went to francium, and francium exploded and left the building. It was a big smoke bomb there. So the ionization energy was decreasing as I went down this column of the periodic table. We can see these electron affinities have a similar trend. So they are decreasing in the amount of energy they release. Here I have chlorine, bromine, and iodine. So let's look at those on the periodic, before I switch, let's look at those at the periodic table. See, we also see high ionization energy for chlorine, lower for bromine, lower for iodine. So if I look at those on the periodic table, they're over here. Chlorine, bromine, iodine. Those ionization energies also decrease as I go down the periodic table. And these electron affinities, we're doing the having a similar trend in that they became less exothermic, releasing less energy as you went down the periodic table. So the properties, these properties of atoms, have trends in the periodic table. Ionization energy decreases as you go down. Electron affinity decreases as you go down the periodic table. Where am I on my slide? So we looked at the actual reaction. We'll talk about redox. You know, you're not responsible for that right now. That's just electrons moving around. Let's do a chem quiz related to this. What's the ionization energy of chlorine minus in kilojoules per mole? So think about that for a minute. We'll go into our groups. When you have a screenshot of that, Ryan, we'll start the quiz. So Ryan has the quiz started. She's captured that. So I should have the group of 4 here waiting for you, and I'll hop into one of the breakout rooms. Okay, I'm back. So we were looking at the ionization of chlorine minus. We will go to your thoughts, go to the poll here. See what you're thinking. We're thinking 349, and we're saying 349 with a plus sign. That is, we need to absorb energy for that to occur. And you're saying, I'm pulling electron off, so it's got to be a positive one. I kind of like that thinking. The number 349, where did that come from? Well, let's look. I think you guys have been very clever this morning. What we had on the board here is this reaction. We had chlorine minus. I'm going to go all the way back. We had chlorine minus going to chlorine neutral plus an electron. That was ionizing chlorine minus. Well, Cl minus, X minus going to X neutral plus an electron, that looks a lot like this reaction, but in reverse. So it looks like the reverse of this reaction, and we know the energy for that reaction. So I think I have that in the animation here. So let's look. So we have this reaction, the electron affinity. The reaction we're talking about is the reverse of that. Why didn't I just put the reverse of that in there? Going that way. So we had Cl minus goes to the electron and Cl. So that's the reverse of this reaction, and that reaction has a release of energy of 349 kilojoules per mole. So the reaction going in the other way absorbs that 349 kilojoules per mole. So excellent, good thinking. Here I'm going to summarize some of these atomic properties, the ionization energy and the electron affinity, and it correlates with our structure of the periodic table. And here I've written the structure of the periodic table in terms of the electron configurations. So you can see I'm going across a row here, adding one electron as I go down, carbon, nitrogen, oxygen, fluorine, neon, sodium. I go down one more row to the next row of the periodic table, from row 2 to row 3. And here's the first row of the periodic table, hydrogen, then the second row starting here of the periodic table. And you can see some various trends. I'm going to plot them on the next slide here. We'll plot ionization energies in kilojoules per mole versus the elements as I go across the periodic table in rows. First row 1, and drop down to row 2, and then end up at sodium in row 3. So let's see what those look like. Hydrogen, we have that 1250 kilojoules per mole to ionize hydrogen from its 1s state. We know helium, to ionize that from its 1s state. If it were helium plus the ion, remember, that would be 4 times as much, because the N went up, or Z went up by a factor of 2. So the ionization energy would go up by a factor of 4. But there's another electron there that shields it. So rather than going up by a factor of 4, it goes up by a factor of a little less than 2 there. So interference of shielding of one 1s electron from another. But as we continue, now we go to lithium in the 2s state, and you can see I've gone down in the periodic table, and the the ionization energy has decreased as we thought it would. Now I'm going to continue to go across the periodic table to boron, and then carbon, and then nitrogen. There's nitrogen. So lithium, beryllium, boron, carbon, nitrogen, filling 1s or 2s1, 2s2, 2p1, 2p2, 2p3 by the time I get out to nitrogen. And I see already a trend emerging as I'm going across the periodic table. Ionization energies are increasing. So I went down a column, they decreased. I'm going across a row, and they are increasing. The general trend, we can see a little blip here. We'll see a little blip when we go to oxygen, and then it'll continue up as I go to neon. Neon, the highest ionization energy in that row. It's at the very far end of the row. And then dropping down to sodium, ionization energy in the 3s orbital. So across the periodic table, ionization energies increase. You could look at these steps here. So this step here where we have a little blip, this guy here is nitrogen, 2p3. This guy here is oxygen, 2p4. So why is oxygen a little easier to ionize than nitrogen? Well, you remember the 2p orbitals. So nitrogen looks like that with its electrons all parallel. Oxygen looks like that. So ionizing this electron here that's paired in a single orbital turned out to be a little easier than the ionization of the nitrogen. And I think you could see why that is. If you put another electron, now you have that pairing energy. You're sticking them in the same orbital. So compared to the previous one, this oxygen, this electron is a little easier to remove than the previous one because you've suddenly stuck one in the same orbital. So you can understand why there's that little dip as you go across. And this brings up one of those things that kind of bug me and a lot of people. This half-filled shell, 2p3 for nitrogen. It's half-filled P shell. People say that that is a stable state. I don't like saying that because the stability isn't a thing, really. You have to just compare one energy to another energy. The thing that has the lower energy is the more likely state in nature, so that could be called more stable. I just like to call it the lower energy state. So we can see the relationship. We compare nitrogen to oxygen. Nitrogen was a little harder to ionize than oxygen. So more energy had to put in. That means nitrogen is lower in energy than oxygen. The nitrogen is a lower energy state than oxygen, but it's oxygen's fault, not nitrogen. Oxygen has that extra electron. So it's not like nitrogen has some fancy property. It's just if you look at something compared to that, that thing has higher energy. So this whole idea of stable, I don't like it. Higher energy, and the nitrogen has higher energy. The oxygen has the nitrogen has lower energy than oxygen. You could call that stable. I just call it slightly lower energy. We have to compare it to something, or it doesn't mean anything. You can't just say, oh, that thing has an energy of blah and that's stable. No, you have to say this has an energy here, That has an energy there, so they're different. One is lower energy. It could be called more stable. I'm just going to call it lower energy. And don't let me confuse you. These numbers, I keep saying nitrogen is lower energy. It's higher on this diagram, but this isn't we're not plotting energy here. We're plotting ionization energy. It's harder to ionize nitrogen. It has the higher ionization energy. So if you looked at them on a plot, it would be nitrogen. I have to ionize here. Oxygen is up here. Nitrogen is harder to ionize than oxygen, a bigger ionization energy. So it's lower in energy. But of course, on this plot, it's a higher ionization energy. We're plotting ionization energy. Okay. That's stability ionization energy. So let's do a chem quiz about this. Oops. I haven't said this exactly, but I think you can, we've said this already. Which of the following has the shortest radius? So what's the atomic radius? And I haven't told you this exactly, but I think you're going to infer it from what we've talked about with ionization energies. So which of these atoms is essentially the smallest? It has the smallest atomic radius. So think about that for a second. We will start the clicker and we'll get ready to go here. There's the group of 4 that you can look at. You should have the picture of the chem quiz on your Reef software, your response software. Okay, we are back with the group. Let's see what you guys were thinking. Argon is quite popular than chlorine. So let's look at your thinking here. And I didn't say anything about atomic radius in advance per se. We have talked about the fact that as you get to larger n, that is farther from the nucleus in general. So N1, N2, N3. So that's some indication of what's going on. That trend of getting farther from the nucleus should be reflected in ionization energy. And we saw that already. So let's look at this and discuss it together. So we're talking about atomic radius now, and we've got chlorine, argon, and potassium. So chlorine is 3p5, argon 3p6, potassium 4s. So if I look at the periodic table, can I have the periodic table, Ryan? If I look at the periodic table where these guys are, I have chlorine, argon here, and then potassium here. So I had the 3s5, 3s6, and then 4s1. So going across here, I see the same principal quantum level, 3, another charge on the nucleus, but in the same principal quantum level. And here I go to the next principal quantum level. As I was going across, I know that that ionization energy was increasing, getting harder to pull things apart. One of those reasons is those atoms are getting smaller. Radius is going down. Why is that? Well, I'm in the same principal quantum level, level 3, but I just added another plus charge to the nucleus, going from chlorine to argon. So the electron, maybe it was in 2p and you put another one in the same 2p, but the whole thing, so 2p5 and then paired, spin down 2p6, well, you also put another plus in the nucleus. So that 2p was there, put another plus on the nucleus and another electron. The overall effect is that plus charge pulls the whole atom together. So an electron kind of in the same region of space, 2p up, 2p down, more positive charge, pulling them closer together. So those guys got smaller. And then I go to a whole nother shell now. I go out to n equal 4. So here I was in n equal 3. And then I go to n equal 4 here when I get to potassium. So chlorine and argon, I got a little smaller, ionization energy increased, and then I got bigger because that next electron went in the next principal quantum shell. And that's reflected in the fact that potassium has the higher ionization, the lower ionization energy. That electron went farther from the nucleus in the 4 principal quantum level. Pulling that off was easier than sodium. So the ionization energy increased as I went across and then dropped as I went down to potassium. And we saw that in our plot, and we see it reflected in the relative sizes. So I bring up sizes in that as a result, something you can infer from the ionization energies. So indeed, when you look at this, argon is the smallest. It gets smaller as I go across. We understand that ionization was getting higher. Ionization energy was getting higher. Then I went to potassium in the next principal quantum level. So let's go back, and we can see that the electrons are adding here in this principal quantum level, but the atoms are getting smaller. The ionization energy is getting bigger. But then when you go to the next level, from 2 to 3, I see a big, for goodness sakes, I see a big jump in ionization energy, a big change, because that electron is in the next principal quantum level, farther away, easier to ionize. So those two trends correlate with each other reasonably well. So which of the following has the lowest ionization energy of these three we have here? So now we have to put all of this together with the ions, their sizes, what you would expect them to do. So think about that for a second. I'll put the periodic table up. Go ahead, take this one, Ryan. Okay, so they're started, they can see it. And then you'll have to go back to the periodic table for us. You guys are all online, so I kind of expect you could have a periodic table open. And there's a much better one that I'll use as well. But let's talk about this chem quiz together in our groups. The ions and atoms we're talking about on the board. Oops. One of them was chlorine, one of them was argon, and one of them was potassium. The same we talked about in the previous one, different charges. I'll join a group. Okay, we're back with the group. Let's see what they're thinking. That's hilarious. That just appeared coincidentally under my annotations. Most of us are thinking A, that, and I forget which one was A. Was it potassium plus that was the A? I think, no, it was chlorine minus. We were thinking was the A value. I have to go back to the chem quiz, so let's do that so I can remember what's going on. You guys are thinking chlorine minus has the lowest ionization energy, the easiest to ionize. Let's go through your thinking on that. I think I like your thinking. Here's the ionization energy. You probably noticed that all of these have the same number of electrons. Argon has 18. Chlorine neutral had 17, but you added one. And you went to argon. Stay there. Stay there. Potassium had 19, but you took one away. So we'll look at the periodic table. Oh my goodness, we are really behind. So there's the periodic table. I had chlorine with 17, but it's chlorine minus. So it's 18, looks like argon. Potassium is 19, but it's potassium plus. So it has 18 electrons. So all of them have the same electronic configuration, the same arrangement of electrons. So with the same arrangement of electrons, what should win? The number of plus charges in the nucleus. So the number of plus charges in the nucleus is what did I do here? Number of lowest. Okay, yes, sorry, lowest ionization energy. Yes, chlorine has the lowest. The most protons are potassium, so chlorine has the lowest. Sorry, I was thinking of the most protons in the nucleus, and that is potassium. But the easiest to ionize is the one with the least protons in the nucleus. That's chlorine. All right. So here's a general summary of our trends and a new property, electronegativity. Electronegativity is a property that isn't measured by experiment. It's not something like electron affinity or ionization energy where you can do a specific experiment. Electron affinity is you look at lots of molecules and you say, in the molecule, I have two atoms, two elements. Do the electrons spend the same amount of time around both of them? And it's hardly ever the case. Usually electrons favor one nucleus in the molecule over another. And that favoring, electrons favoring one over the other, is called electronegativity. The higher your electronegativity, the more electrons tend to favor you as an element in bonds. So electronegativity is the relative, in a bond, the relative attraction for electrons. So elements that have high electronegativity draw the electrons to them in a bond compared to another element. So that trend generally goes from the diagonal across the periodic table to the highly electronegative here. They're very attractive to electrons. When in this upper corner, these are not generally attractive to electrons. So in bonds, these elements have more electrons around them than these elements. And that leads to something called polarity. So here's some differences in this value of electronegativity. Sodium chloride, the difference in electronegativity between those two is around 2 units of electronegativity. And that is a large difference in electronegativity. That means chlorine very strongly draws electrons over sodium. And we can understand that. Sodium on this side, chlorine on that side. And chlorine draws them so much more that it draws the entire electron, one full electron, away from sodium. And this is an ionic bond. Ionic means ions are formed, a plus ion of sodium and a minus ion of chlorine, and that attractive plus minus energy attraction holds sodium chloride together. That's the strongest possible bonds you can have, are when you actually pull one electron and put it on the other thing, and you get pure Coulombic plus minus attraction occurring. That makes a very strong interaction, and it's multiplied tremendously by the fact that then it makes a crystal of all pluses and minuses together and really pulls it together tightly. You know, sodium chloride is a crystal. Here's partially ionic. So I have electronegativity differences between about 0.5 and 2. HCl is a example of that. It's strongly polarized. The electrons are strongly pulled towards the chlorine, but it's not fully ionic, not one full charge pulled over to the chlorine. So I write these little symbols, these little delta symbols. Darn it. Going to go to my annotate here. I write these little delta symbols. This is a little bit of charge, a fraction positive and a fraction minus, not a full positive and a full negative like in the ionic bond. So this is a polar bond, and you would notice you could, if you're drawing kind of a sketch of electron probabilities, it would be low here and high here. A little bit more negative over here, more negative charge there, and less negative charge, partial positive charge near the hydrogen. Delta for partial plus and partial minus. Then when the electronegativities are very close, the difference less than half a unit, we call those purely covalent interactions. Covalent means a very good sharing of electrons. One element isn't more electronegative significantly than the other. So electrons can spend about equal proportions around the molecules. And that is perfectly the case if they're the same element. So obviously there's no electronegativity between chlorine and chlorine. So that's perfectly covalent, perfectly symmetric covalent interaction. Here's a fun one. I mean, you guys are nailing them today. So see if you can nail this one. So I have hydrogen molecules and some other diatomic, either Cl2, Br2, or I2 here in the X. The reaction is going to make HXs. So break those bonds, form those bonds. If I do that, which releases the most energy? If it's Cl2, Br2, or I2 forming HCl, HBr, or HI. So think about that. Got that captured. And once you have it captured, you go to the periodic table. And I'll flip back and forth between the chem quiz and this. Okay, we're back with the group. We're running out of time, but I have office hours starting now anyway, so we'll just continue. So the thinking here among the group is a lot of us are thinking A, that's chlorine. So am I clipping? Yeah, blue is still got blue lights over there. Okay, so is there a little echo? Okay, so let's go back to the PowerPoint, and you were thinking that the HCl has the most polar bond because of those positions in the periodic table. Can you hit 24 enter? You're ready? This drawing is a little lame. So why is HCl the most polar, and why is the most polar bond the strongest? So we already said the more charge separation you get. Oh, wait. I can think about this better if I have my cerebrum on. So this picture is not that good. Let's go to Ryan's picture of the periodic table because I have the ions or the elements in slightly the wrong place. So chlorine, bromine, iodine, the most electronegative is the chlorine, then I get less electronegative and less electronegative. So the more polar bond is the ClH. They're all bonded to the same thing. So ClH is more polar than HBr and HI. That greater polarity is leading to a greater bond strength. And that greater bond strength is related to a bond energy. So HCl is the most polar. HCl would be the hardest to pull apart. So that means it would be the best at putting together. It would release the most when you put it together because it's the hardest to pull apart. So I agree with you. Whenever you break a bond, it always takes energy. If you take nothing else home from Chem 1A, take home the fact that breaking bonds requires energy. And that one you can take to the bank. Some things there's always a caveat and a maybe this and a maybe that. No, you break a bond, you always have to put energy in. You're pulling those things apart. That means making bonds always releases energy, and making the bond here released the most energy when you were Cl. What was happening on the other side was always similar, pulling apart the H and the homonuclear bonds on this side. Okay, fantastic. We'll stop there. We should have got a little further. We'll get a little further Monday. Any questions? We have office hours starting now anyway.
Is that why HCl?
The question, is that why HCl is strong? It's an acid that's in our stomach. It helps us digest food. Actually, that's not quite the answer. The answer there is acid strength rather than direct bond strength. So it's slightly different. We should have said maybe that this is in the gas phase, that this is gaseous chlorine and gaseous hydrogen forming gaseous HCl. So it's not even in the liquid phase. So HCl in a liquid phase, the HCl can come apart and form H pluses and Cl minuses. And that interaction of the H pluses in your gut is what helps break down food, break bonds in your food. It's actually a really neat thing, and we'll talk about it more. I'm glad you brought it up because we have this HCl, and I just told you that was a strong bond. We're going to put it in water, and it's going to break apart. And that's what I should have mentioned. This is the gas phase, HCl. And when you put it in liquid, some other factors come into play, and we'll talk about those later. It does not change the fact that it still takes energy to break a bond. Other questions? Pretty quiet?
When will the midterm one answers be released?
Oh, I thought we released. The question is,
I held off because I wasn't sure if that one student took it yet. We can do that.
oh, okay. I'm sorry. The question is, when will the midterm answers be released? I thought they were. I'm sorry. We talked about it yesterday, and the student instructors are telling me I wasn't listening. So we'll release them. We do it right now. We can do it right this second. Melissa's going to push the button right now. I think we were waiting for, we have people in Russia, Moscow, all over the world taking it, and everybody had not finished the exam, and there was a couple people that had internet problems and had to retake it. So we didn't post it just because of that. But I think everybody's done, and Melissa's releasing them in real time. You can go to B Courses right this second and check. And by answers, we mean you can click on your quiz. It's the midterm quiz, and it'll show you what you answered and what the correct answer is. Other things, Ryan? I think there was another question.
These are from earlier in the lecture. How does electron shielding contribute to the dips in the graphs, or does it contribute to the dips?
In the electronegativity plot. So I'm live here, right? So I can do this. There's a question about that trend. Is this not me? Oh. There was kind of a question about how does I'm sorry, how does what affect what? How does shielding affect these trends in energy? And there's the big gross overall trend, and that is the s electrons are good shielders of the p electrons. So these ionization energies, it's getting these ionization energies are increasing as you go across. The p electrons are not particularly good shielders of each other. So they're not particularly good shielders. So each p electron as you go across is kind of seeing more positive charge because its buddy p's in the same level aren't shielding the nucleus very well. All the shielding is coming from the s's, and the s's shield all the p's about the same, but the p's don't shield each other very well. So you have, as you go across the periodic table, these guys aren't shielding each other very well. So each one is effectively seeing another positive charge. So Z effective is kind of marching up because you're adding p electrons and they don't shield each other very well. So you get plus, another plus charge, another plus charge, another plus charge, and another plus charge as you go across. The little dip there didn't come from effective nuclear charge. The little dip at oxygen came from the fact that you paired an electron in a p at that stage, and that's a little higher energy. So if you're a little higher energy, it's a little easier to ionize. So your ionization energy went down. Another question?
Can you talk about the difference between energy and ionization energy? Can an element be at lower energy level but have higher ionization energy?
The question is, can I talk about energy and ionization energy? I love that question. I mean, this whole thing about where the energies are, it does get confusing, and I absolutely sympathize with you when I say ionization energy and then I say energy of the system. Those seem like disparate things. So can you, Ryan, tell us what slide that is? It looks like it might be. It's the big picture of that 16. Okay, so go to, and the periodic table was what, 24? Okay, we have to look at the whole thing. I just wanted some space. Oh, wait. I know what I can do. Let's be clever. That's okay. I'm going to be more clever than that. What I'm going to do is I'm going to take a picture of just that, and I'm going to put it on the whiteboard. Cool. And I think you guys like the whiteboard better when it's a blackboard. Okay. So I keep talking about energy and ionization energy. So remember when we had the quantum systems, we had energy going, oopsie, I have to change myself to a pen. We had energy going as n. So it was, we had the energy of the system as a function of n, the quantum number, and that was going like minus z squared over n squared, and there was a constant in there, Rydberg constant. So this is the energy of the system if we're talking about a positive and a negative charge being attracted to each other. So plus z charges attracting an electron. And those energy levels we saw, they're easy to plot out. So energy plotted here, and these are the various levels of n. So this is an energy state, and an electron can have this energy state, but energy, and we said this at the beginning of the class, energy has to be measured relative to something. So energies don't mean anything as numbers unless they're relative to something. In this case, these energies are all relative to the zero of energy that we put right there. So when I say this energy, and this energy for this lowest level is E of level 1 is minus z squared times r, because n is 1. So that's just 1 squared is 1. So that amount of energy from here to here is z squared minus z squared r relative to 0. Okay? It's a negative energy. It's below 0. It's a low energy. And I say it's a low energy because it's low relative to these other states. So saying low energy is relative to something else. Now, you could have energy levels in other systems, and we saw the particles trapped in space in a box. Those energy levels started at 0 and went up. So here, this was a low energy state relative to this energy state. We could also put everybody relative to 0 if we wanted there, and then compare them. But comparing them to each other, here is a high kinetic energy state. Here is a low kinetic energy state. In the lowest particle in a box, we had low energy states, all of them positive. But we have to measure them relative to something. This guy here is not a low energy state unless you compare it to something else. This guy here isn't a low energy state unless you compare it to something else. Or you have a universal standard of 0. So that's the idea of the energy in the system. Now, when I talk about ionization energy, that's the energy of a reaction. So I start out with some energy, and then something happens, and there's an energy change. Ionization energy is an energy change. Something happened, and the thing that happened was your H atom, let's say, went to an H atom with a plus charge and an electron with a minus charge. That's a reaction. That's a process. This reaction has an energy associated with it because hydrogen has an energy state. It's in this energy state here. Hydrogen with it's an electron. Hydrogen plus E minus is up here at 0 energy. And that's weird to think about. I'm saying that that has 0 energy. But again, magnitudes of energy are relative. This has 0 energy relative to that. This doesn't have 0 energy in the big picture of things. These hydrogen pluses and E minuses might be moving all around the place. They might have kinetic energy, blah, 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 blah. Relative to this, this has 0 energy. So and that's simply because we define that to be 0 energy, just so we can do our bookkeeping. Let's call that 0 and measure everything relative to it. So when this happens, this amount of energy either has to be supplied. I have to put that much energy in. This is a delta E right here for ionization. Here, that energy numerically is equal to the energy of this state, because the energy of this state is measured relative to 0, and you have to put in this amount of energy to go from here to 0. But the ionization energy is a delta E. That's a process. The system, this system has energy. The system here has energy minus Z squared times R, and this has energy 0. It's just relative numbers. The ionization energy is a process. It's a delta E. This is an energy relative to something else on our scale. So this is an energy you can have, a energy of the system. This is a change in energy. All have to be measured relative to something. And I absolutely admit that takes a long time to think about, and it gets worse because I draw stuff like this. And when I draw stuff like this, to stop being a pen for a second. When I draw stuff like this, I'm going up here. Oops, don't delete. No, don't. Come back to a pen. I'm drawing these ionization energies, and these ionization energies are getting higher, a larger number, but these states are going down in energy. So that is inherently confusing. So carbon, so we're going carbon, nitrogen, oxygen. So carbon, we'll draw the carbon energy level. I'm just drawing it arbitrarily somewhere on the board. 0 in energy is way up here somewhere on the board because that's when everything is pulled apart. Carbon is here. That's an energy. Now, nitrogen is here. So let's make it obvious here. Carbon, nitrogen, oxygen. So carbon, nitrogen, oxygen, I have this scaling in energies. These are energies you have to put in to pull off an electron. These are not the energies of the systems. These are the energy changes. How do they relate to the energy of the systems? Well, carbon, it takes this much energy to ionize. It's something like 1,100 kilojoules per mole. Nitrogen, something like 1,400 kilojoules per mole. So it takes more energy to ionize nitrogen than carbon. So that means this energy going from here to the top, that ionization energy is bigger for nitrogen. Well, 0 stays at the same place. So how do I make carbon relative to nitrogen? Well, if this has to get bigger, nitrogen has to be down here. Okay? And that's the source of the confusion. You go, oh, well, that's going up in this plot, but that reflects these things going down in energy because this gap to go to 0 is getting bigger. Okay? That's a lot to absorb. It's kind of why we started the class with, let's talk about drawing energies and relative energies. So I was hoping that would sink in. And I'm not saying it didn't. I'm saying we're going crazy fast. So it's hard for anything to sink in. But I wanted to start with the idea of energies and changes in energies because, like I said, when we started there, we're going to do it for the rest of the course. Okay? Other questions?
A student asked if you can go over another question similar to this one. First quiz that we did today.
So there's a question, can we talk more about ionization energies? And what we did is we looked at ionization energies with respect to the photoelectrons that are coming off. Yes, so Melissa, can you tell us what slide number that is?
Lecture 12, slide number 15.
That doesn't help us because I don't think we're in lecture 12. That's okay. Ryan can find it. So there's a question. Yeah, you can find it and you can bring it up when you have it displayed. There's a question about ionization energy and photoelectrons. And Ryan has put example on her screen. So we'll look at her screen. Her screen has a lot of stuff on it. And I'll do the same kind of thing. I'll just take a little picture of just part of it. Well, we can keep the answers in there. Get rid of all the rest of that crap. And I think I can erase all my little marks. So the question was, what about questions like this? Can I kind of go over something like this? And something like this is something like this. This is changing shells and seeing how the ionization energy changed. When we did this one, we had hydrogen, 1 electron in principal quantum level 2. So we know we can draw hydrogen in those principal quantum levels, and this is n equal 1. That's energy minus r, which is z squared over n squared times r. In this case, both those things are 1. It's hydrogen. Z squared is, z is 1, n is 1. So what you have there is just minus r left. I'm going to erase that so we don't get confused about having both the number and the equation there. Okay. Then we said, well, we have in this case some other species. And in this case, the species, and when I say species, I just mean type, thing. Another species is helium with 2 electrons. How do I know it has 2 electrons? Because there's an electron configuration for it. This is helium 1s1, 3p1. 2 electrons. So it has both of its electrons. This 1s, we're saying, is a very good shielder of the electron in the 3p. So for He in this configuration, Z effective, that is the effective nuclear charge that this electron sees out in the 3p, is very close to 1, because this electron in the 1s very effectively shields that. And I want to make this very clear. The charge on the nucleus did not change. Different electrons see different amounts of charge. For every single electron in an atom, you could calculate a different Z effective. It's just the charge that that electron happens to see. So if you have a 30 electron atom, there's 30 Z effectives, 1 for each electron. So this isn't a set fixed number. It's how does that electron you're talking about see the nucleus? So this electron we're talking about is the 3p electron, and we're saying the 1s. So we have helium with its 2 plus charges in the nucleus, and we have its 1s electron there, and we also have its 3p electron out here. These are the probability distributions of electrons. I'm not going to draw 2 because there's only 1. These are the probabilities of finding that other electron. These electrons see only 1 plus charge because S electrons are very good shielders. The charge that that guy sees is +1 because this guy shields one of them. This guy, his Z effective is 2 because he sees both those charges, and this p electron is a horrible shielder of him. So his Z effective is pretty much 2. His Z effective is pretty much 1. So there's a different Z effective for every single electron. In this case, his Z effective is about 1. That means his energies look just like hydrogen, whose Z is 1. So that electron in the 3p, this is n equal 1, n equal 2, n equal 3. That is an electron that looks just like a hydrogen electron. There's that electron. And this first electron here, we'll do it a different color. That species, oops, I drew it in the 1. It's in the 2. So that hydrogen system, that electron has this energy. This electron, that 3p electron, has this energy. That 1s electron, what energy does it have? Well, it sees the full +2. So that guy, could you guys put, ooh, that's a good chem quiz. Can you guys put that one on this scale? Are they in Zoom? Is the person that answered this in Zoom? Oh. Oh. Okay. Let's keep it open. I mean, someone could physically ask a question, right? They could actually talk to me. I didn't realize we closed. I guess we closed the Zoom. Is anyone watching the live stream? Am I talking to anyone? Okay. I hope the person that asked this question is out there. The people who are there are very lucky because they have a little bit extra time. Okay, lucky might have not been the right word. They get to see more of this. So We have 2 electrons here. The 3p we're putting here because we're saying that looks like a hydrogen because that one s electron is shielding one of the positive charges. Where's that one? That other electron? Well, that's Z's full plus 2. So it goes like Z squared over N squared, and it's in the 1 level. So this one electron here, it has energy. It's in the 1 level. So it's Z squared over N squared. N is 1. Minus sign with that. N is 1, but Z is the full 2. So 2 squared is 4. So it's minus 4 R. There's the Rydberg over there. So that guy is way down here, minus 4, off the board. I don't know what the picture looks like. Probably if I do here, you can't see it. But it's down off the board. Those 2 electrons have different Z effective, so they have wildly different energies. So the question was, what's going on here? How do I ionize them? Well, there's one more species. It's the same argument now here. Lithium has two electrons here, so it's easy to draw lithium. There's another positive charge in the nucleus, but it's 1s2, so there are 2 electrons down there in the 1s. They effectively shield the 4p electron. And I've drawn a 3p. 4p would be farther away. 4p is up 1 principal quantum level. It would also have some radial nodes going through it. I'm sure you're thrilled to hear about those. 4p is bigger, so it would be farther away. And it would be in this higher energy state. So this electron here also has Z effective equal about 1 because these 2 are very good shielders of it. Very good shielders of the plus charges in the nucleus. So that is a situation where all these electrons, that one, and that one, all have Z effective of about 1. So we can scale them as this guy in principal quantum level 2, that guy in principal quantum level 3, that guy in principal quantum level 4. So then you have to say, how much energy would it take to ionize them? Well, if this is how much energy it would take to ionize that one, then this is a great chem quiz where you could see this on the exam. You could see me saying, oh my God, you could see me saying this point lies on the line of hydrogen's ionization curve. Can you draw helium 3s or 1s1 3p1 on that same curve? Where would the point have to move to get onto that curve? I know you're just like cringing. I never want to see that. But that curve, well, this guy sees the same effective charge, but he's in a higher state. He's here. He is easier to ionize. It's less energy to get up here to 0. Less energy. So if it takes less energy to ionize, that's the energy that just gets the electron off the atom. That's the energy where it just starts to move. That means this guy, helium, its curve must be back here. And the most direct way to get from here to here, if you're keeping frequency constant, would be to move straight up to here. I could also ask you the question, if that's keeping frequency constant, what if I was keeping wavelength constant? I won't be that cruel. You could also get to that point going that way, but I'll make it clear when I ask the question which direction you have to go. Frequency constant, you'd have to go up. Okay. So what about this guy here? What about lithium? Well, that guy is in the 4. So he's even easier to ionize. So his ionization energy is even lower frequency. And he's out here. I love that. That's going to be on the next exam. The people who go to office hours always get lucky because people ask me questions and I go, oh my God, that should be on the exam. Okay. Any other questions out there coming in? There's a question clarifying on the graph. Why is there UV here? That stands for ultraviolet. It just means this frequency, remember these are photon frequencies, that's a frequency that corresponds to ultraviolet radiation. And I'm saying that these energies are less than that. That means they would be visible when you get lower energy than the ultraviolet. That doesn't matter for anything I said, that UV. All I need to know is that was the energy it took to ionize the hydrogen. That was this energy. That means this energy, the green one, was this energy, smaller. And this energy that's yellow was this energy, smaller yet. That's all I needed to know. I didn't need to know for what we've discussed that was UV. Anything else? Okay, guys, that was fun. I'm glad some people stuck around to ask questions. Brilliant questions. Keep them coming. We'll see you tomorrow.